Hello, my name is Jangwan Choi, and I'm going to talk about the paper simplifying graph convolutional networks. The table of contents is as follows. And this simplifying graph convolutional networks paper by Felix Wu presented at the ICML in 2 years ago. This work is popular and widely cited in GCN field due to its simple method. First, before dealing with simplifying graph convolutional network, SGC, we should know about the background of the GCN. GCN, graph convolutional networks, are an efficient variant of convolutional neural networks on graphs. Recently, GCNs and subsequent variants have achieved state-of-the-art results in various application areas, including but not limited to citation networks, social networks, applied chemistry, and computer vision. And GCNs were proposed after the recent renaissance of neural networks, and they tend to be a rare exception to this trend. So, GCN inherit considerable complexity from the deep learning lineage, which can be burdensome and unnecessary for less demanding applications. Even GCNs are built upon multi-layer neural networks, and these GCNs were never an extension of a simpler linear counterpart. Now we can define the problem statement, which is previous GCNs inherit unnecessary complexity and redundant computation. So the objective is to reduce the excess complexity of GCNs, but maintain the model accuracy. So this paper aims to derive the simplest linear model that could have preceded the GCN had a more traditional path been taken. And they repeatedly removed the nonlinearities between GCN layers and collapsing the result function into a single linear transformation. And I'm going to introduce GCNs and subsequently SGC in the context of node classification. And there are two stages of GCNs. The first is feature propagation, and the second stage is feature transformation and nonlinear transition. And this is the notations for GCN domain. This red bounding box is the feature propagation. And here, this equation, at the beginning of each layer, the features h sub I of each node v sub I are averaged with the feature vectors in each local neighborhood. And this equation is the simultaneous update in equation below for all nodes becomes a simple sparse matrix multiplication. And this S matrix is the augmented normalized symmetric matrix. And intuitively, this step smooths the hidden representations locally along the edges of the graph and ultimately encourages similar predictions among locally connected nodes. Next, this red bounding box is linear feature transformation. After the local smoothing, the GCN layer is identical to a standard multi-layer perceptron. And each layer is associated with a learned weight matrix, this theta, and the smoothed hidden feature representations are transformed linearly. Finally, a nonlinear activation function, such as ReLU, is applied pointwise before outputting feature representation, this H. In summary, the representation updating rule of the case layer is here, this equation. Now let's see simple graph convolution. This SGC finds that utilizing only a simple logistic regression here after feature propagation and removing the nonlinearities activation function like ReLU. In GCNs, the layers have a second importance function. In each layer, the hidden representations are averaged among neighbors that are one hop away. This implies that after k layers, a node obtains feature information from all nodes or k hops away in the graph, like this figure. And this part is the linearization of SGC. First, the paper hypothesizes that the nonlinearity between GCN layers is not critical, but that the majority of the benefit arises from this local averaging. They therefore remove the nonlinear transition functions between each layer and only keep the final softmax in order to obtain probabilistic output. And the resulting model is linear, like here, but still has the same increased receptive field of a k-layer GCN. To simplify notation, we can collapse the repeated multiplication with the normalized adjacency matrix S into a single matrix here by raising S to the k's power like this, as superscript large K. Also, we can reparameterize the weight into a single matrix theta, and the resulting classifier becomes this equation. And this red box is feature propagation, and the blue box is the linear classifier. I'm gonna skip this 3 slides because I already mentioned before. But I will only mention this part and move on to the next slide. This SGC applies multinomial logistic regression with parameter theta to predict the node labels. And now that's it. This section is the spectral analysis. The first order Chebyshev filter derived in GCNs corresponds to the propagation matrix, this large S. And since the normalized Laplacian is here, then this equation is changed to this equation like this. Thus, the filter coefficient with kth order becomes like here, and this Laplacian denotes the eigenvalues of symmetric Laplacian here. And the figure below is the filtering operation relative to the first order matrix, this F, for a varying number of propagation steps. The high powers of this first order S lead to exploding filters coefficient like this figure, and undesirably over-amplify signals at the frequencies lambda sub I is less than 1. Correspondingly, we define the augmented normalized Laplacian like here. Thus, we can describe the spectral filters associated with symmetric normalized adjacency matrix as a polynomial of the eigenvalues of the underlying Laplacian. On the figure above Here, symmetric normalized adjacence matrix corresponds to filters in the spectral range from 0 to 2. Therefore, odd powers of normalized adjacency matrix yield negative filter coefficient at frequencies lambda is greater than 1 here. But by adding self-loop, the augmented normalized adjacency matrix, the largest eigenvalue shrinks from 2 to 1.5 and then eliminates the effect of negative coefficient. Moreover, this scaled spectrum allows the filter defined by taking powers k is greater than 1 of augmented normalized adjacency to act as a low-pass type filter. And this is the advantage of SGC. And this section is the experimental result. And this table 2 shows the performance of SGC. And this SGC can match the performance of GCN and state-of-the-art graph networks on citation graphs, Quora, CiteSeer, and PubMed. In particular, CiteSeer, SGC is about 1% better than GCN, and we reason this performance boost is caused by SGC having fewer parameters and therefore suffering less from overfitting. And here, on Reddit dataset, Table 3 shows that SGC outperforms the previous sampling-based GCN variant like Sage GCN and Fast GCN by more than 1%. And this part is the performance of the state-of-art graph networks over their training time relative to that of SGC on the PubMed and Reddit dataset. SGC minimizes memory usage, and SGC only learns a single weight matrix during training. These two figures show that SGC can be trained up to orders of magnitude faster than the fast sampling-based method here. And this part is the conclusions of the paper. And the above figure is the key part of the SGC, key figure of the SGC, because SGC reduces the complexity through successively removing nonlinearity functions, and by pre-computing the fixed feature extractor, this augmented normalized matrix with superscript k, training time of the model is reduced. And then this paper shows SGC from a convolution perspective and manifests this method as a low-pass type filter on the spectral domain. From this analysis, they provide insight into the empirical boost of the renormalization trick, which is augmented normalized adjacency matrix. And the experimental evaluation demonstrates that SGC's simplifications do not negatively impact accuracy in many downstream applications. And that's it. I think that this paper is a starting point for future research in graph learning, which means that it is returning to the historic machine learning practice to develop complex from simple models. Thank you for listening to my presentation. Thank you.